Welcome everybody. In this video I'm going to talk about incorporating molecular biophysics into the undergraduate curriculum. And I'm going to start by talking about skills that are needed for students using Excel, and then we'll talk about how to communicate about how to do things in Excel using algorithms. One of the main mathematical techniques we're going to use is modeling change using finite difference methods. Then we'll talk about how students can validate models that they've developed by comparing them with real experimental data, doing curve fitting and data analysis. A major challenge for us is to try to make thermodynamics more interesting to life science students. And a couple of the ways we'll do that is talking about osmosis and the chemical potential of water, ligand binding and saturation, and binding energies and the Boltzmann factor. At the end of the talk I'll talk about ion channels and how the Nernst potential can be explained in a simple way. And that'll lead to traditional physics descriptions of the same situation using batteries in an equivalent circuit and the action potential. And if we get time, we'll talk about how the same techniques can be used for modeling COVID-19. Now, switching over to my PDF here, I have a picture of the marble game, which is a simulation of diffusion in which marbles jump from one box to another using a random choice selected by a dice, and they can jump one way or the other way, and again each jump is randomly chosen with no bias. Those jumps actually simulate the Brownian motion of molecules in solution, and I have here a little simulation. It's a three-dimensional one with 50 molecules in a box, and when we start it you can see that all 50 of them start jiggling around executing Brownian motion, and after some time they have a chance of jumping from their original box into box one, but they can also jump back. It's a random choice, and that's what the jumps actually simulate. Alright. So how do students start out? Well, they look at that video and see how it relates to Brownian motion, but we actually start at the very beginning in Excel with learning how formulas work and how Excel works. And to give you a flavor of how that actually is done with students, let me show you a spreadsheet that students write for themselves. It's very straightforward. I've pretty much filled in most of it and done the graph. And the way this spreadsheet works is we have column A for the turn, which just counts, and it uses a formula for that. The second column is the random number R, and it's calculated using the Excel instruction ran between 1, 200, so it simulates rolling a 200-sided dice. And then N1 is the column where we keep track of how many molecules are in box 1. We start out with 0, and then the main instruction for the marble game is that it just equals, and we use the Excel function if the random number that we rolled is less than or equal to the number that are already in box 1, then the value that we get is the old value in box 1 minus 1, i.e. 1 leaves. Or if it's the other way round, we get the number in box 1 plus 1. And then close paren, hit enter. And one of the nice things about Excel is that you can highlight the row and then left double click, and it copies it all the way down to the bottom of the spreadsheet. And when you hit delete in a blank cell, Excel recalculates the simulation and you get a fresh instance of the marble game. And so students can see how random choice results in some variability, but overall the trend is fairly predictable. Alright, so here are the algorithms that I talked about. They have a number of features that, just to highlight them, students have parameters that go in column A, variables that are headings for the row, for the main part of the table. Step 0 is setting up, and step 1 is the main part of the algorithm. Alright, so once students are okay with doing spreadsheets, we then introduce them to using finite difference methods, which predict what happens on average in the simulation. And so jumps from box 1 to box 2 are given by this rate, which n1 is the number in box 1 and k is the jump rate constant. And this arrow indicates jumps from box 2 to box 1, and again n2 is the number in box 2 and k is the jump rate constant, which is the same in both directions because of the unbiased nature of the jumps. Now, the finite difference equation, this little delta means a small change in n1. So the small change in n1 is given by the blue arrow is leaving, so it has a minus. n1 times k comes down to here. Delta t is the small amount of time that we're thinking about, the time step. The plus here is because the red arrow is going into box 1, and that's n2 times k times the time step. And students can rearrange that to get this finite difference equation, which can be implemented in a spreadsheet. And in a guided inquiry exercise, students compare the predictions of the marble game, the stochastic model, with the finite difference method for the ensemble average behavior. And so here's the spreadsheet, and as you can see, it has the kinetic Monte Carlo version of the marble game, which when I hit delete in a blank cell, it updates and shows different versions of it. The gray dashed line here shows the ensemble average prediction that you get from the finite difference method, and you can see that the blue line tracks along that, sometimes a little higher, sometimes a little lower, but on average it actually tracks along the grey line. And students can investigate many things from this spreadsheet, but one of them is that you can increase the number of particles in the system, and you can see that the results become more predictable and more closely follow the grey line in every instance. All right. So, using similar techniques, students can investigate a new model of osmosis, and the hypothesis that they're going to test is that osmosis is the diffusion of water across a semi-permeable membrane. And the idea is that the diffusion occurs through an aquaporin protein, and there's a selectivity filter here where the water goes through in single file. And the way that it does that is through a diffusive process where the net effect is that a yellow one comes into the end of the file and a red one pops out the other side. And of course, the whole process is reversible. Using that model, students can come up with a finite difference model of osmosis into a red blood cell, which is an example that's quite familiar to students. And then they can compare that with data that was actually collected as part of a project that ended up with the Nobel Prize. Then they can investigate what happens if there's a pressure difference across the cell membrane, which can happen when you've got plant cells. And that pressure difference introduces an energy difference, which is just PV work for a water molecule to go from low pressure to high pressure. And by incorporating that in the kinetic model using a simple energy factor, students can show that the diffusive model of osmosis correctly predicts the Van't Hoff equation, which can be written in two ways. One using kind of the traditional osmolarity difference for delta S, and the more mechanistic way is to talk about the effective water concentration, so there's a minus in there. In Chapter 6, we use the same kind of methods to talk about ligand binding, and the example that I choose is oxygen binding to myoglobin. And students can show that using simple algebraic methods that the average occupancy, theta 1, is the occupancy of the myoglobin molecule, the probability that it's full, is given by this Hill equation. And they can test the predictions of the model by comparing it with experimental data by using the least squares fit for the sum of the squares of the residuals. And I have a little sample spreadsheet here just showing that fit. And so the spreadsheet here has Q here is calculated as the sum of the squares of the residuals that are calculated in this table. And by clicking on the Data tab and then using Solver, students can find the smallest value of the capital KD binding parameter to make the theoretical curve go along and through in a least squares way through all the data. All right. And so using similar mathematical techniques, they can actually derive the Michaelis-Menten equations for enzyme kinetics, in this case sucrase, and they can compare the same equations for enzyme saturation. They can also add the energy using a Boltzmann factor for the binding of oxygen to myoglobin, so the bound state has a lower energy, and they can derive this equation, which can then be fit to experimental data for myoglobin oxygen binding at a variety of temperatures, and by doing that they can find the dissociation enthalpy. The same techniques can also be applied to membrane voltage and ion channels using a similar mechanism, and students discover that the potassium ions, as they go diffuse through the ion channel, they come out here, but they're attracted back to the cell membrane because they're attracted back to the negative counterions that they left behind. And in that way, the cell membrane acts like a capacitor, and students can then model the action potential by opening sodium channels, then potassium channels, and then finally chloride channels to get back to the resting potential. And that can actually motivate the traditional circuit theory models of ion channels. And unfortunately, we don't have time to talk about how the same techniques can be used to model COVID, but you can check out this paper on arXiv, which I recently posted. All right, so getting back to PowerPoint, the summary of what they've done, the students have been use a guided inquiry approach with self-study guides. The students are actively involved in their own learning because they're doing activities. There's an emphasis on skills, reading and interpreting graphs and semi-log graphs, fitting models to data, using FD models to model the rate of change, which can lead to calculus if that's one of the things that you have in your curriculum. And students can get thermodynamics from kinetic models, which I think makes thermodynamics more interesting. And so in summary, in the guided inquiry environment, students can discover for themselves that science is an evidence-based endeavor with testable hypotheses that are supported by real experimental data. And for further information, you should go to circle4.com/biophysics and look for the links at the top of the page.